Hi everybody, in this video I want to show how the Galileo formulation of relative velocity violates Einstein's second postulate of relativity, which says that the speed of light is the same for all observers. I'll then go on to introduce the Einstein formula for relative velocity, and then finally at the end of the video I'll show how the Einstein formula reduces to the Galileo formula in the case of speeds that are slow compared to the speed of light. Okay, so here we go. I'm going to start with this prior example that I did in another video. So imagine I'm taking the positive x direction to the right. I've got a turtle going to the right relative to the ground with a velocity of 0.03 miles per hour. I've got a person moving relative to the ground to the right with a velocity of 1.0 miles per hour. All right, so I've got the velocity of the person relative to the ground. I've got the velocity of the turtle relative to the ground. And what if I want to know the velocity of the person relative to the turtle? Well, we use the Galileo/Newton relative velocity formula. Velocity of the person relative to the turtle is the velocity of the person relative to the ground plus the velocity of the ground relative to the turtle. And you can construct this for any three objects that you're comparing. In this case, we've got person, turtle, and ground. You just have to get the subscripts lined up. First subscript here matches first subscript here. Second subscript here matches second subscript here. And this third subscript links. Okay, so for the velocity of the person relative to the ground. And again, these are x components, right? I've left off the x component notation so that we don't have subscript overload. But you always, when you're applying this formula, have to choose a coordinate system, have to choose signs of your components in the context of that coordinate system. All right, so velocity of the person relative to the ground is positive 1.0 miles per hour. Velocity of ground relative to the turtle, well, that's not specifically in here. I've got the velocity of the turtle relative to the ground. Relative to the ground, the turtle is going to the right at 0.3 miles per hour. But from the turtle's perspective, the ground is moving to the left at 0.3 miles per hour. So the velocity of the ground relative to the turtle is minus 0.3 miles per hour. Right, so just keep in mind, anytime you flip the subscripts on the relative velocity, you change the sign. All right, so what do we get for the velocity of the person relative to the turtle? We get positive 0.7 miles per hour, which means that the person is closing in on the turtle at 0.7 miles per hour. And once the person passes the turtle, they'll be getting ahead of the turtle to the right at 0.7 miles per hour at that rate. Great. Let's now see what happens when we apply the Galileo formula for relative velocity to a situation that involves light. When we do that, we'll see that the Galilean formula violates Einstein's second postulate of special relativity, which says that the speed of light is the same for all observers. And I want to note that while this postulate was originally something that Einstein imagined theoretically in order to, among other things, resolve a contradiction in electromagnetic theory, this postulate has been now experimentally verified by over 100 years of experiments. All right, so I'm going to use c to represent the universal speed of light. That's the symbol that's usually used for the universal speed of light, which turns out to be about 3 times 10 to the 8th meters per second, or 300 million meters per second. All right, so now I'm going to use analogous numbers, but instead of miles per hour, I'm going to use fractions of c. So imagine I've got the ground. I've got to the right again as my positive x direction. I've got a light beacon that's shooting out light. So imagine this is a little light particle. And I've got the velocity of the light relative to the ground is 1c. Great. Now imagine I've also got a UFO zooming to the right relative to the ground. U for UFO. Velocity of UFO relative to the ground, let's say that's 0.3c, 3/10 of the speed of light, to the right. All right, so both of these are positive because they're both going to the right relative to the ground. And I want to see what the Galilean formula gives for the velocity of light relative to the UFO. All right, so here we go. The x component of the velocity of the light relative to the ground is 1.0c, positive. The velocity of the ground relative to the UFO, well, look, first, the velocity of the UFO relative to the ground is 0.3c to the right, but the velocity of the ground relative to the UFO is 0.3c to the left. If the UFO is going to the right relative to the ground is going to the left relative to the UFO. Hence, I've got a minus sign in there. Minus 0.3 c. And in general, anytime you flip the subscripts of something in a relative velocity, you change the sign. Okay, so we add these up. We get plus 0.7 c. Now, what have we calculated? We've calculated the x component of the velocity of the light relative to the UFO. And that came out to be 0.7 c. But Einstein's second postulate of special relativity says that the speed of light is the same for all observers. So this needs to come out as c. It came out as 0.7 c. So we have a contradiction. This Galilean formula contradicts Einstein's second postulate. So I'm not going to derive the Einstein formula for relative velocity. What I'm going to do is write it down and show that it resolves this contradiction. I'm going to show that the Einstein formula for relative velocity at least gives the right result for the velocity of light relative to the UFO. All right, so first I'm going to write down the Einstein formula, and then we'll plug in the numbers and see how it works. All right, so here we go. Okay, so here's the Einstein formula for relative velocity. It looks very similar. Velocity of the light relative to the UFO. I have the first subscript here matching the first subscript there, second subscript here matching second subscript here, and then the third subscript links. So that much, just the numerator, is very similar. It's exactly the same, basically, as a Galileo-Newton formulation. But now I have a denominator, 1 plus this velocity goes here, that velocity goes there, divide by the speed of light squared. All right, so this has units of speed times speed divided by speed squared. This little chunk right here has no units, so when you add it to 1, it has no units. All right, so the denominator has no units. All right, so let's see how this works out. Let's see if this resolves our contradiction. So if I want to use this formula, the Einstein formula, to get the velocity of the light relative to the UFO, I can plug in. So I've got the velocity of the light relative to the ground. That's plus 1.0 c. I've got the velocity of the ground relative to the UFO. Well, that's going to be the negative of the velocity of the UFO relative to the ground. We're flipping subscripts. So I've got plus a negative 0.3 c. And then in the denominator, I've got 1 plus. Now these same velocities go here as we're here. So this one goes there, this one goes there. So I've got 1.0 c times minus 0.3 c all over c squared. So let's see what we get. 1c plus a negative 0.3 c gives me plus 0.7 c. And then look at the denominator. I'm going to have c times c divided by c squareds. So all those c's will cancel. I'll have 1 times a negative 0.3, which gives me negative 0.3. Then I'll have negative 0.3 plus 1, which will give me 0.7. So I get 0.7 c divided by 0.7. That gives me, for my answer, c, which is what I want. The Einstein formula gives me that the velocity of the light relative to the UFO is positive c. Now, if we turn this around, we had it all going the other direction, I could get negative c. So the velocity could be positive c or negative c. Speed of light has to be the absolute value of that, 3 times 10 to the 8th meters per second, or just c. All right, so this Einstein velocity formula for this example gives a result consistent with Einstein's second postulate for special relativity, which says that the speed of light is the same for all observers, and that speed of light has to be c. The last thing I want to say is that the Einstein formula isn't just something that's limited for use at high speeds. The Einstein formula actually is general. It can be used for all speeds. So to show that, I want to show that the Einstein formula actually works for this example in which we use the Galileo-Newton formula. So to convert this to the Einstein formula, All I have to do is divide by this denominator. So let's do that. So I'm going to erase this. And to turn this into the Einstein formula, I'd have 1 plus, then I'd have these things in the denominator. 1.0 miles per hour and minus 0.3 miles per hour over c squared. Now, c is 3 times 10 to the 8th meters per second. If I square c, I'm going to have 9 times 10 to the 16 meters per second. I could convert these to meters per second if I want. That's just going to be a few meters per second. So I've got a few meters per second squared divided by 9 times 10 to the 16th meters per second. For all intents and purposes, all of this is going to be 0. This divided by basically 1 gives you this. So the Einstein velocity not only works for high speeds, it also works for these ordinary speeds that the Galileo and Newton formula works for. All right, so I want to emphasize this. Some people think that the Einstein formula only works for high speeds. It actually turns out the Einstein formula is general, and that if you take the limit, the low speed limit, the Einstein formula reduces essentially to the Galileo formula. All right, I hope that helps. Thanks for watching.